So the final topic in our first set of slides is called l'Hopital'sRule. Rule. And this is a rule for evaluating limits. So it's just one more little piece of what we started on the first session. And so the problem that I want to look at is, suppose I have a function that looks like this. So I have sine x divided by x. So one of my rules said that for a rational function, I could just think of this as the limit of the top divided by the limit of the bottom. But that's not going to work here for two reasons. A, the limit of the bottom is going to 0. So it's a continuous function. It's going to be 0. And the limit of the top is also a continuous function, and sine of 0 is 0. But if you plot this thing, it looks like this. So it looks like it's very well defined, except if I plug in the number 0, I get an undefined quantity at exactly 0. But any positive number or any negative number, it's well defined, and it looks like this. So if you wanted to sort of fill in the gap, so I'm missing this one little point right here, there's a very obvious choice of what number you would want to choose to put there. And so this is sort of the problem if I just tried to evaluate it using the rules I already know. But that's not allowed since the denominator is equal to 0. And so l'Hopital's rule lets us make some sense of this. So let x be a real number, or plus or minus infinity. And let f of x and g of x be differentiable functions. And there's a lot of conditions, so this is a little bit longer than I would like it to be to fit on a slide. But basically what it's saying is, if the limit of f of x, so this is the thing I'm going to have on the top of my fraction, is 0, and the limit of g of x, so the denominator of my fraction, is 0, and if the limit of f prime divided by g prime exists, and that just has to be true on some neighborhood around x0. So you can imagine a point to x0, and then there's a over here and b over here. So you have some points around x0. And you need g prime, so the thing on the bottom has to be non-zero everywhere except at x0. Then the limit of f of x over g of x, so this is not the derivative anymore. This is the two original functions. So this could be sine x divided by x as x goes to 0. It exists, and it's equal to the limit of the derivatives as x goes to x0. And I think this will be more clear once I show an example. And then we also have pretty much the same thing if I have a rational function, but in this time, instead of going to 0, so 0 over 0, now it's going to infinity divided by infinity. So this is another quantity that I can't make any sense out of mathematically. But pretty much the same conditions. So if f prime over g prime exists, and I have this, so the intervals now just mean after a certain number it has to hold, so such that g prime of x is not equal to 0. Then the limit exists, so f of x over g of x, even though both of these are going to infinity, the limit exists, and it's equal to the same thing, just the limit of the two derivatives. And then just a note so you can use this slide for reference in the future. So if x0 is plus or minus infinity, then these intervals that I've been writing, x has to be in the interval a, b, you would just think of as minus infinity up to b, or a to infinity. So the way we're going to use this is if I want to now try and make sense out of the limit sine of x divided by x. So I have the limit of the numerator and the limit of the denominator both going to 0. So if I just try to evaluate this, or sorry, since they both go to 0, I'm allowed to use l'Hopital's rule. So I can say that this limit is equal to the limit of the derivative of the numerator divided by the derivative of the denominator. So we've already shown, or already said, that the derivative of sine is cosine. So the limit here is going to be equal to the limit as x goes to 0 of cosine x divided by 1. So the derivative of x is just 1. And now this is a continuous function, so I can just plug in the value 0, and I get cosine of 0, which is equal to 1. And if we go back quickly and look at my picture, that's exactly the value that I would want to choose for this function to make it continuous. Oops. Okay. So as another example, consider x squared minus 1 divided by x squared plus 1. And I want to look at the limit of this as x goes to infinity. So clearly the numerator is going to go to infinity and the denominator is going to go to infinity. So if both of them go to infinity, I'm allowed to use l'Hopital'sRule rule. And that tells me that this limit is equal to the limit of the derivative of the numerator divided by the derivative of the denominator as x goes to infinity. And so when I take the derivative of the top, the derivative of the minus 1, 1's constant, so that's just going to be 0. And the power rule says that the derivative of x squared is 2x. So I'm going to end up with the limit as x goes to infinity of 2x divided by 2x. But still, I can't, this isn't continuous at the point where I want to. Or, sorry, I'm not going to 0, I'm going to infinity now. So still, if I look at the limits here, the limit of 2x divided by the limit of 2x as x goes to infinity. So I'm kind of struggling here to show you that you can use l'Hopital'sRule rule twice to get the same thing. You could just cancel the x's here and be finished. But the idea here is if you end up, after one application of l'Hopital'sRule rule, with another rational function that's still 0 over 0 or infinity over infinity, then I can go ahead and use l'Hopital'sRule rule again. And so I end up with where I was before, take the derivative one more time, so now I end up with 2 over 2, and that's always going to be equal to 1, regardless of x, so the limit as x goes to infinity of that is going to be 1.